Okay, so now that we have an idea of local continuity in terms of how it's viewed in an analysis, let's do this for an actual example. And for this one, we're going to do this at one specific point, so we're going to just make a equal to an arbitrary value. So in this case, let's let a equal to pi. So the problem says to let f of x equal 1 over x and let the domain be from 0 to infinity, show that f is continuous at a is equal to pi. So anytime you get a problem like this and you're wanting to write a proof for it, you always want to start out with side work. You don't want to jump straight to the proof because you need the side work to give you all the leggings to put into your proof. So let's start the side work. So the side work, again, you're always going to want to state let epsilon be greater than 0. I explained in the previous video, whenever we were talking about continuity in terms of analysis, I explained why epsilon has to be greater than 0, and I also explained why you want it to be arbitrary. So if you missed that, go back and check out the previous video where we talk about just kind of the basics of continuity in terms of analysis. But the side work, you always want to state let epsilon be greater than 0. And to fulfill the definition of continuity, we want to seek a delta greater than 0 such that the absolute value of f of x minus f of pi in absolute values, that difference is going to be less than epsilon if x minus pi in absolute values is less than delta and x is greater than 0. Now again, I told you in the previous video that x is very important for pointwise continuity. And x has to be stated as greater than 0 here because x has to be in the domain, and 1 over x we all know is discontinuous at 0. So if you let x be equal to 0 or less than 0, you're going to have problems with pointwise continuity. So you always want to state that x is in the domain. So in this case, x has to be greater than 0. So how would we start our side work? So we're going to start with this fact right here. We want to start with that and we want to unload that. So we're going to say f of x minus f of pi in absolute values. What is that equal to? Well, you literally just plug in numbers for this part. So that's just 1 over x minus 1 over pi. And now you just want to do a simple common denominator or something you've done since elementary school. So put those two together and you're going to end up with x minus pi. And in the bottom numerator is going to be x times pi. And this top part, you're going to want to have it in absolute values because you want, again, this entire term right here is an absolute value term. And if you look at the definition, you want x minus pi in absolute values from the definition. So you want to make sure that you have this absolute value there. It's actually really important. The denominator, we don't care that much. You can write an absolute value there if you want to, but pi is just a constant, it's always positive, we know that, and we already stated in our definition that x is greater than 0, so x is also positive, a positive times a positive, it's always positive. So you don't have to state the denominator's absolute value, but you're more than welcome to if you're more comfortable doing so. So we get to this point just with basic algebra, just plugging and chugging numbers and getting common denominators. So what do you do once you get to here? This is probably where a lot of people get stuck because after this you kind of have to have a little bit of intuition with how to write these proofs. So ultimately what we're looking for is a delta value. That's what we're seeking. We're seeking right here in the side work. We seek a delta greater than 0. So we need some sort of delta that's positive. So this is where kind of the voodoo math magic comes into hand because we're just going to make up a delta that's positive. Let's just let delta be equal to 1. And again, that's arbitrary. If you want delta to be 1/2, if you want delta to be 100, it doesn't matter. As long as delta is greater than 0, and it's arbitrary, so it can be anything you want it to be. As long as it's positive, it'll work. But I'm going to choose a super simple constant like 1. So now, what do? Well, we know from our definition that we want x minus pi in absolute values to be less than delta. So we can say, okay, well we have x minus pi. Oops, why is it doing that? So we have x minus pi, and we set delta to be 1. So we're going to say it's less than 1. So now if we translate that absolute value, we know that pi minus 1 is going to be less than x, which is going to be less than pi plus 1. And then if we translate that again, we know that pi squared minus pi is going to be less than pi times x, which is going to be less than pi squared plus pi. Now why did we do that? Well, you've got, and let me get a different color here. So this right here that we have in red, that's what you have to work with. You know that this numerator, this x minus pi, from the definition, that's already bounded by delta. So you're good to go there. The only possible issue that you have is this denominator, because this denominator currently is not bounded by anything. So that denominator can blow up. And if this term blows up, you can't force it to always be less than epsilon. So what you need to do, if you get a situation like this, you want to take something that you already know, which is the numerator. We already know that's bounded by delta, and we set delta to be 1. So this right here we already have bounded. And you want to use that to bound something you don't know yet, which is this denominator. So we want to bound this. That's our end goal right now. Now if you want to bound a denominator, obviously if the denominator gets big, the entire term gets small, which is good. For our situation, it's good because we want everything to be less than epsilon. So if you make something smaller, that's good. However, if that denominator gets really, really small, as in if x gets really, really, really close to 0, which in our case it's allowed to because you see that the domain is from 0 to infinity, so you can get infinitely close to 0. And as x gets infinitely close to 0, the denominator gets really, really small, so this entire term blows up. So we want to bound this to where the denominator is only allowed to get so small, and it can't get any smaller than that. So you have this inequality down here, but you're going to want to use this side. Because if you use this side of the inequality, you know that that pi x term, the smallest that it can possibly be, is pi squared minus pi. It has to be bigger than pi squared minus pi. So pi squared minus pi is the absolute lowest that can ever be. It can never be smaller than that. So that's what we're going to want to use. And we're going to want to invert this because we have pi x's in the denominator. So we're going to invert this. And let me switch back to black. So if you do 1 over pi squared minus pi, and then you have 1 over pi x. And remember, if you invert fractions like that, you need to flip the sign. So it's going to be like that. So you're going to have 1 over pi x is always smaller than 1 over pi squared minus pi. So what does that tell us? We just did all those little manipulations. We made up a delta term. What does that actually tell us then? Well, now we know that f of x minus f of pi, I don't know why I just did that. Let me fix it. F of x minus f of pi in absolute values. By definition, that's equal to x minus pi in absolute values over pi x. That's by definition. We did that just a second ago. But now we know that that is always less than x minus pi in absolute values divided by pi squared minus pi. And again, we just showed that with our inequality. We just showed that this was always true. But this inequality that we just wrote right here, this is only true if this x minus pi in the numerator is less than 1. Because if you look back at the top, and I'm going to circle this, point this out in blue, our whole case we just made was based on letting delta be equal to 1. And we started with this inequality. Let x minus pi absolute values be less than 1. So this inequality down here that I'm circling in blue, that is only true if x minus pi in absolute values is always less than 1. So you have to state that in your proof. You're going to have to use that.
No, this is
but now we have one more thing, because if you look back at the definition, you know that you want this f of x minus f of pi in absolute values. You want this to always be less than epsilon. So you're always going to end with this whole term being less than epsilon. But just like this inequality only happens in certain conditions. And this one is going to be if x minus pi, that's x minus pi, sorry for my bad writing. If x minus pi is less than epsilon times pi squared minus pi. That's epsilon pi squared minus pi. Again, sorry for the bad handwriting. Now, why is it epsilon pi squared minus pi? Well, if you look back right here, right there in that thing I just boxed in blue. So you know that this has got to be less than epsilon. We know that, right? If this is true, you can move this denominator, you can throw this up here, and you can have pi squared minus pi times epsilon, and have that be less than this 1 over pi x. And if you do that, you get to this point right here, where this x minus pi in absolute values has to be less than epsilon times pi squared minus pi. Hopefully that makes sense. If it doesn't, pause this and kind of go back through the inequality, and you'll see that if you do this, this whole inequality works out, and you'll get back to the very beginning where this x minus pi has to be less than epsilon, which is what you're wanting altogether. So we've got all this messy side work. How do we actually write a formal proof? So I've already typed this up ahead of time, so I'm just going to show you how we did this. So once you do the side work, all you have to do, the side work is the heavy lifting. Writing the formal proof, you just have to take all the little pieces of the side work and word them in the correct way. So our formal proof, you're always going to start with suppose epsilon is greater than 0. That's a basic fact of how you prove continuity, so you're always going to start with that. Epsilon is greater than 0, epsilon's arbitrary. And again, we're not proving uniform continuity. That's a separate thing. We'll get into that in a few videos down the road. And so since this is not uniform continuity, this is continuity at a specific point, you have to state that that x is in the domain. And we're doing that at the very beginning by saying x is greater than 0. And now, the two deltas that we just found. We found that delta, we said that delta, right here, we said delta was equal to 1. And then down here, we also said that delta could be this epsilon times pi squared minus pi. So you want to state that epsilon is greater than 0, x is greater than 0, and delta is going to be the minimum of 1 or epsilon times pi squared minus pi. Epsilon's arbitrary, so you don't know which one of these is smaller. It depends on what the value of epsilon is. So that's how you want to state that. And you want to put those three statements at the very beginning of your proof. So now you just want to start unfolding the definition. So if x minus pi in absolute values is less than delta, and again, that's just from the definition of continuity, then this f of x minus f of pi in absolute values is equal to 1 over x minus 1 over pi, which is equal to x minus pi divided by pi x. And that is just by definition. That's what we did at the very beginning of our slide. We just plugged in x, we plugged in pi into 1 over x, and we found a common denominator, got x minus pi over pi x. Just by definition, it's just algebraic fact. And then from the side work, we proved that that was always less than x minus pi, and there should be an absolute value there. Don't know why there's not. X minus pi over pi squared minus pi. But that is only if the absolute value of x minus pi is less than delta, which that delta we set equal to 1. So that delta has to be less than or equal to 1. And again, this is coming directly from our side work. So this, let me get the pen again, and I'm going to put it in green. So this statement right here is coming directly from this fact right here. This is where we started the side work. So we set delta equal to 1, and then we started unfolding this absolute value to get all this information. So that is where we threw it in down here at the bottom. That's where this is in green, this is where we threw that information into. It's right here. And then, like I was just explaining, we know that this is also less than epsilon, but that is only if this x minus pi in absolute values is less than delta, and that is when delta is less than or equal to this epsilon times pi squared minus pi term. And again, that part came directly from this right here. So again, this piece of the side work goes right here, and the delta being equal to 1 is right here. And then you're done, because you've proven that if you bound this x minus pi in absolute values by an arbitrary delta term, then you can also bound this f of x minus f of pi value by an arbitrary epsilon term. And that's the definition of pointwise continuity. So then you can draw this big fancy box like this that says you're done with the proof.